Okay, so what we're going to do is we're going to write electron configurations for magnesium and argon using both the SPDF and orbital box notation. For getting the electron configuration, the best way to do it is to use the periodic table, and you want to break the periodic table into subshells. So this is the 1s subshell, this is the 2s, 3s, 4s, 5s, 6s, and 7s. And here, these are D subshells. And these are P subshells. And I can tell my pen's running out of ink. So this is actually part of the 1s. And this is a 2p, 3p, 4p, 5p, 6p, 7p. This is a 3d, 4d, 5d, 6d. And this down here, and this is a 4f and a 5f. So this is called the S block. This is called the D block. This is called the P block. And this is called the F block. If you want to get the electron configuration of an atom, let's say it's this one right here, which happens to be aluminum, what you do is you read the blocks until you get to that particular element. And when I say that you read the blocks, is you actually start off with the electron configuration with the block that you first start at. So this would be 1s. And then you look at how many cells you have to go over in that block. And here we have to go over 2 cells. So you'd start off with 1s2. And the 2s is the next subshell you run into. And you have to go, through 2 cells, 2 elements to get to where you're going. The next one you go into is the 2p. So here's the 2p. And there are 6 cells. And then you go to the 3s. You go through 2, and then you get to the 3p. And since aluminum is the first element in the P subshell, 3p subshell, you write 3p1. So what these stand for respectively are shell, subshell, and this stands for electrons in that subshell. Okay, so using this idea here, let's get the electron configuration of magnesium. So magnesium is right here. And reading across, you get for magnesium 1s2, 2s2, 2p6, and then 3s2. And there's your electron configuration of magnesium. Now, when they ask for the orbital box diagram, the orbital box diagram originates from this idea that these subshells are filled differently because they have different stability. The 1s is more stable than the 2s, the 2s is more stable than 2p, and so forth and so on. And I discuss why they're different in stability in lecture and in the last Q&A. But suffice it to say that all 1s are more stable than all 2s. All 2s are more stable than all 3s. All 3s are more stable than all 4s, so forth and so on. That's the stability order, but the filling order doesn't quite follow the stability order. Nonetheless, if we look at the stability order, here is the 1s subshell right there. The 1s subshell has only 1 orbital in it, and that's what that line represents. Sometimes people draw a box there. The 2s has 1 orbital, so there's the orbital. The 2p has 3 orbitals, so you draw 3 boxes. The 3s has 1 orbital, so you draw 1 box. The 3p has 3 orbitals, so you draw 3 boxes. And the 3d has 5 orbitals, so you draw 5 boxes. So this is an order of stability, where this is more stable and this is less stable. And when you put electrons in these boxes, you put them in as arrows. So here for this 1s2, it would be 1 up, 1 down. You always put 1 up first. The 1 up means plus 1/2. The down means minus 1/2. So the 2s, you do this. Now, when you're putting these into the 2p, you put one electron in first to each orbital. You don't pair them up at the beginning. And the reason you don't pair them up is because electrons repel electrons. And if you put them in the same orbital, there's a slight repulsion there. If you put them in different orbitals, there's less repulsion. So we put them in different orbitals. And then we put the other 3 in. And since we have no choice, we pair them up. 3s. So this would be the orbital box diagram for magnesium. However, most likely when you see the orbital box diagram for magnesium, it will look like this. So we write it horizontally because that's how we write on paper. And this is more stable and this is less stable. So there is also, well, that's it. Now it says, describe the relationship of the atom's electron to its position in the periodic table. If you look at where magnesium is in the periodic table, right here, it is at the end of subshell 1s, 2s, 3s, the end of subshell 3s. And because it's at the end of 3s, it should have 2 electrons in it, which means it's full. So any element that ends here in this particular group is going to end in S2. So this ends in 2s2, 3s2, 4s2, 5s2, 6s2, 7s2. So they're all going to end in an S2. All right. If you're okay with that, let me know. A lot of this should seem like review because you've done it before in high school. Okay. Let's take a look at the next one here. Using SPDF notation, give the electron configuration of vanadium. So I'm going to flip my piece of paper around here. And here's my periodic table. Vanadium is right here. So for this one, it's the same as before. We're going to follow the filling order, but then we have to do something extra. So if we look at the filling order, we start at 1s, 1s2, and then we go to 2s, 2s2, then we go to 2p, 2p6, then we go to 3s, 3s2, then we go to 3p, 3p6, then we go to 4s, 4s2. And if we look at vanadium, it's there in 3D, 1, 2, 3. It's the third one over, so 3D3. And this is mostly correct, but partially wrong. When we write the electron configuration, after you get the filling order, you rearrange it to the stability order. So I said before that 1s are more stable than 2s, 2s more stable than 3s, 3s more stable than 4s. Here we have a 3 after a 4, which is no good. So we write 1s2, 2s2, 2p6, 3s2, 3p6, 3d3, 4s2. And always when you write them in order, it's always S goes before NS, goes before NP, goes before ND, goes before NF. So if you're looking at the third shell, a 3s goes before a 3p, goes before a 3d. Okay, so this is the correct electron configuration of vanadium. This is mostly correct, but it is partially incorrect. Any questions there? Are you okay with that one? Are we good, Harry? So the directions are basically to read, that's the filling order, and then rearrange, and that's the stability order. And sometimes you don't have to rearrange. Like for magnesium, we didn't have to rearrange. Okay. So this says using SPDF notation. Let me flip my paper here. Using SPDF notation and noble gas notation, write the electron configurations of strontium. So here's what they mean by SPDF notation and noble gas notation. We get to go ahead and start at a noble gas. So here you can well imagine that if you have the electron configuration of neon, sodium is going to be the same as neon, but with the addition of a 3s1. So you could write the electron configuration of sodium as neon 3s1. This is called the SPDF noble gas notation. There's also the orbital box noble gas notation, in which case this would look like this. Are there any questions about the noble gas configuration combined with either SPDF or orbital box? Are we good with that? Okay, so let me show you how to get there. So we're asked to do strontium, and strontium you can see is where? Right here. There's strontium. So if we go back to the previous period, we can see that we can start at krypton. So for strontium, we're going to start at krypton, and then we're just going to read from there. So here's krypton. When I go down, this is 1s2, 2s2, 3s2, 4s2, 5s2. So strontium is in the 5s subshell. It's the second element in the 5s subshell. So we get krypton, 5s2, and we're done with strontium. Now, if we had yttrium, it would be krypton, 5s2, and you have to go over here to the D subshell. This is a 3D and this is a 4D, so that would be a 4D1, and then you'd have to rearrange it to krypton, 4D1, 5s2. So with the noble gas SPDF, you still have to do a rearrangement if necessary. And if you do the noble gas orbital box, you still have to do arrangement if necessary. Are you guys okay with that? Okay, well then here, your job is now to write the electron configuration for zirconium. Actually, do more than zirconium. Let's tackle let's tackle these three: zirconium, rhodium, and tin. And remember, we're doing the noble gas configuration. So if you don't already have your book open to the periodic table, you should do that soon. And give me a little hands up when you're done. Remember to give me the thumbs up when you're done. Oh, I got rubidium, not rhodium. Where's rhodium? Okay, we're going to talk about these. Go ahead and turn on your mics. I'm going to point at a subshell. You tell me what it is. So you see this H, that would be 1s. Okay. So I'm going to point at a subshell. You tell me what it is. What's that?
1s.
What's that?
2s.
What's that?
3s.
What's that?
4s.
Okay. So we're doing the Japanese way of learning, which is to look at something, decide what it is, and say what it is, and then repeat. And it turns out that it works. So what's this?
4s.
Okay, say it like it's an answer, not a question. What's
Oh,
this?
it's 4s.
Jackie?
4s.
Okay, this one.
5s.
That's 5s.
That sounds like a question.
That's 5s.
This one.
That's 6s.
This one.
That's 7s.
Let's try again.
That's
1.
1s. 2s.
Come on.
3s.
I can't hear you, Jackie.
4s.
4s.
5s.
5s.
6s.
6s.
Let's try and do it together.
7s.
7s.
All right. So now let's try again. Here, this is the 2p. So what's this one?
2p.
2p.
This one.
3p.
3p.
This one.
4p.
4p.
5p.
5p.
6p. 7p.
7p.
So they go in order. I mean, isn't
Right.
that beautiful? They don't skip any numbers except for they skip the 1p because there's no such thing as a 1p. So what do we start with? What's
So
this?
it's 2p.
2p.
What's this?
3p.
3p.
This one.
4p.
4p.
This one.
5p.
This one.
6p.
This one.
7p.
See,
7p.
that's not bad. Now,
Nope.
there's no such thing as a 2D. So guess what the D starts with?
What? 3d?
3D. So guess what this one is?
3d?
3p.
4d?
4d.
5d?
Correct. That sounds like a question, Harry.
Oh, is it 5d? Sorry, 5d.
5D. How about this one?
6d.
6d.
Okay. And there's no such thing as a 4D. So guess what the 4s start with? Or guess what the F's start with? Let me say that again because I said it wrong. There's no such thing as a 3F. So guess what the F's start with?
4f?
4F. This is a 4F. If this is a 4F, what is this one?
5f.
5f.
5F. So here's how you count them. 1S, 2S, 3S, 4S, 5S, 6S, 7S. 2P, 3P, 4P, 5P, 6P, 7P. 3D, 4D, 5D, 6D. 4F, 5F. You should be able to do that just like I did in 1 minute. So I'm going to give you 1 minute to practice and then we're going to do it. Is that clear?
Yep.
Okay. So you can turn your mics off when you're practicing. Give me a thumbs up when you're ready. Okay, then let's go to it. Turn your mics on. I'm going to trip you up though. Are you ready?
Yeah.
Okay, here we go.
3d.
Harry,
Oh, 3d. Is that what was 30?
4D.
40. 5D.
3D.
60.
6D.
See how I'm tripping you up? I'm not starting with the 1S.
Yeah.
Yeah. How about here?
2P.
How about here?
3P.
How about here?
4P.
4D.
How about here?
5P.
How about here?
6P.
6D.
How about here?
7P.
How about here?
4F.
How about here?
5F.
How about here?
3D.
How about here?
1S.
How about here?
4S.
4S. How about here?
3P.
3P.
How about here?
5D.
5D.
5D. So now let's get the electron configuration of zirconium, which is right here. Do you see that we start with krypton because it's the noble gas before it?
Yep.
Okay, so what is this?
5S.
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 2.
So 5S2. What is this?
4D.
4D.
4D. So how many elements into it to get to zirconium?
2.
2.
So 4D2. Do we need to rearrange?
Yes.
Okay, and so we rearrange and we get krypton, 4D2, 5S2, and we're done. So by knowing where these things are, we can get the electron configuration very quickly. So let's do this rhodium. I have rubidium here. It's supposed to be rhodium. So what is the noble gas before rhodium?
Krypton.
Krypton. So this is right after krypton. What am I pointing at here?
5S. So
5S. Okay.
2.
And what am I pointing at
5S2.
here?
4D.
4D.
4D. So we would write 5S, 4D, and we have to go all the way through the S. How many through the D? Is it like 6?
I think it's 7.
I got 7.
Okay.
You're 7.
So we rearrange and we get krypton, 4D7, 5S2. Any questions there? If none, let's take a look at 10. The previous element is krypton. So let's read. What am I pointing at with my finger? It's right above my finger.
5S.
5S and how many?
2.
Okay, now right above my finger, what am I pointing at for this whole row?
Is 4D.
4D and how many?
10.
10.
10. And then what is this right here?
5P.
5P.
Okay, let's check. 2P, 3P, 4P, 5P. 5P. Excellent. 5P, how many elements in is 10?
2.
2.
2.
So
Yep. 2.
here, when we rearrange, we get 4D10, 5S2, 5P2. Any questions? Okay. Now, these next two are really tough because we have samarium and ytterbium. So here is samarium right here. And here is ytterbium. So I'm going to show you how to get samarium, and then you need to get ytterbium, right? Now, to do this, I'm going to zoom in on the periodic table a little bit. And let me see if I can focus. Okay, what I want to point out to you on this periodic table is this, that here is where lanthanum begins. This should be lanthanum, and this should be actinium. And do you see how lanthanum is written below here? And you see that thick line there? That thick line means that the 4F actually begins with cerium, and lanthanum is back here, part of the 3D, 4D, part of the 5D. So lanthanum is in 5D, cerium is in 4F. Are you guys clear?
Yeah.
Okay. Now, notice lanthanum is number 57 because barium is 56, lanthanum's 57, and cerium's 58. So here, when we read, we have to read by atomic number, not just across the rows. So if we look at our table here, we're basically going to go to this lanthanum, or excuse me, we're going to go to this lanthanum, which is in 1, 2, 3, 4, 5, 6. We're going to go to right here, lanthanum, and then we're going to go to here, and then we're going to go to samarium. Okay, so here we have to skip from the 5D. Whoops, you can't
As
see
you
what
zoom
I
out,
just
yeah.
wrote. So what I've written here, I'm going to have to zoom out, is we have to skip from the 5D down to the 4F. So we don't write 5D10 because we don't go all the way through it. So the previous noble gas in this case is xenon. So we're going to start with xenon. And what we're doing right now is samarium. We're going to start with xenon. And then we're going to go 6s2, 5d1, and then drop down to the 4f. And samarium is 1, 2, 3, 4, 5, 6. It's 6 elements in, so it's 4f6. And this is what we call a reasonable electron configuration. Turns out that it's not right, but it's darn close. And this is what I expect you to be able to do on the test is get something like this. And actually, I'm going to cross this off and I'm going to write this 4F6, 5D1, 6S2, and I'm going to point to that. So after it's been rearranged, that's a reasonable electron configuration. So any questions about how I got samarium? Okay, your turn for ytterbium. So ytterbium's right there. What's the electron configuration of ytterbium? Did you get it, Harry?
Oh, yeah.
Okay, that's why your thumb was up. How are you doing, Jackie?
I think I got it as well.
Okay. Well, let's take a look then. Ytterbium. So it's going to be xenon, 6s2, 5d1, 4f13. Now, how easy is it for me to see that that's 4f13? Well, I know the last one is 4f14 because it's 14 wide. So rather than go 1, 2, 3, 4, 13, I just go 14, 13. Are you with me there?
Yep.
It's just easier to count from the other side and count down than it is to count up. So we rearrange this and we get xenon, 4f13, 5d1, and 6s2. And this is a reasonable electron configuration. Now, the fact of the matter is these electron configurations are probably different. So samarium is probably this, 4f6, 4f7, 6s2, and ytterbium is probably this, 4f14, 6s2. So do you see what I did there? Now, the reason behind this, so this is experimental. And these up here are by filling order. The reason we skipped the 5D altogether and we put all the electrons here in the 14 or half in the 14 is that the F subshell has 7 orbitals. And the D subshell has 5 orbitals. So Ds are definitely a little less stable than Fs. So what we've really done here is we've taken this 5D and we put it down here and put it there for this guy right here, samarium. We took the 5D and put it down there, and we still have the 6s up here. Okay, so why is this more stable than having an electron over here? And the answer is simply this, that if you look at these 10 electrons, or I should say 8 electrons, and your choices are the following. So here's the following. If your choices are this on the left or this on the right it's better because these 8 electrons are evenly spaced in a subshell. That means they can't get more stable than that. Electrons don't like electrons, so you spread them out as much as you can. Now over here, there is 1 orbital that's empty, which means you have 7 electrons shoved into a space that is smaller than a full circle or a full sphere. There's 1/7 of that space, which is off limits to any electron. And when you're trying to distribute charge, that amount of space is important. And when you keep charge out of it, that's something that costs money or costs energy. So this is called the symmetry argument. Now, what are you responsible for on the exam? You're responsible for getting the reasonable configuration. You are not responsible for getting the weird configuration. Is that clear? Okay. However, if I give you a weird one, you're supposed to be able to figure out what it is. So what has the following electron configuration? So this is a weird electron configuration. What is it? When you think you have it, give me a thumbs up. Okay, it's taking you too long, so now I'm going to show you how to do it. Are you ready? Okay, here's how you do it. Do you see that we start at radon, right? Do you see that there's 7 electrons here and 2 electrons here for 9 electrons total, right? So we start at radon, and then we go and we count over 9 elements. 1, 2, 3, and this drops down here, 4, 5, 6, 7, 8, 9. It's americium. So basically what I did here is I said, okay, it's got the same number of electrons and radon has 86. It's got 86 electrons plus 7 plus 2. So 9 plus 86 is 95. And if you take a look at americium, you'll see that its atomic number is 95. So that's how I know it's americium. Are you with me or not? So if you are trying to identify which element it is, because you aren't told, but you are given the electron configuration, the way to figure out what element it is to simply count electrons. However many electrons it has, that's how many protons it has. And the number of protons is on the periodic table. Boom, you're done. Okay, let's take a look at another problem set. So this is about quantum numbers and electron configurations. Okay, what is the maximum number of electrons that can be identified with each of the following? So here's how we go about doing that. For n equal 3, L can be equal to 0. M sub L can be equal to, oops, or L could be 1 or L could be 2. Is that clear? Okay, so we're going back into the previous chapter. M sub L here has to be 0. M sub L can be -1, 0, or +1. And M sub L here can be -2, -1, 0, +1, or +2. So just counting the M sub L's, that tells me how many orbitals we have. We have 9 orbitals. Now, each of those orbitals can have 2 electrons. So that means 18 electrons maximum. So that's how many in the third shell, 18 electrons. Any questions? Okay, how about B? N equal 3 and L equal 2. Well, if L is equal to 2, what can M sub L be equal to? -2, -1, 0, +1, +2. How many orbitals? 5. How many electrons maximum? 10. Okay, let's try C. 4, 1, -1, and +1/2. How many electrons? And the answer is 1. Because when you get down to the M sub S and you're told that it's either +1/2 or 1 -1/2, you're talking about exactly 1 electron. How about D? None. Now, how do I know that it's none? Well, if L is equal to 0, M sub L is equal to 0. It can't be anything else. So this is no electrons. So because M sub L should be equal to 0, not -1. Any questions there? Are we good? If we're good, give me a thumbs up. Okay, let's go down to the next one. Depict the electron configuration of phosphorus using an orbital box diagram and noble gas notation. So we're going to start with a noble gas. And phosphorus is right here. So we're going to start with neon. And I don't go straight to the orbital box. I start with SPDF, even though they say orbital box. So here's the SPDF. We have sodium, or neon, I'm sorry. And then we have 1, 2, 3, 3s2. And then we have 1, 2, 3, 3p2, 2p, 3p, or 3p3, I'm sorry. And now I draw the orbital box. There's no need to rearrange these because we don't have 3s and 4s or anything like that. So here's the 1s, or excuse me, the 3s. And here's the 3p. Notice I give a little space between the 3s subshell and the 3p subshell. The 3p has 3 orbitals, so I draw all 3. How do we put these 3 in here? Like this, 1, 2, 3. Any questions there? Okay, there being none, give a possible set for each electron beyond those of the preceding noble gas. So here we could have N, L, M sub L, and M sub S. We're going to call that guy 3, 0, 0 plus 1/2. Plus 1/2 because it's arrow up. And the guy next to it's going to be 3, 0, 0, minus 1/2. What about this guy? It's going to be a 3, 1. It's a 1 because of the P. And we're going to call it -1 plus 1/2. And then 3, 1, 0 plus 1/2. And then 3, 1, 0 or 3, 1, 1 plus 1/2. That's a little messy. I'm going to cross these off and I'm going to write them over here. So each of these are arrow going up. So I can do this right away for each of those. Each of these are in the third shell. So I can do that right away for each of those. And because it's a P, each of these is a 1. Is, well, what are the M sub L for each of these? Well, if L is equal to 1, M sub L could be -1, 0, or +1. So those are the set of quantum numbers for all three of those in the 3P subshell. Any questions? Or are we good? Okay, moving along then. Do the same thing for titanium. Write the orbital box notation, then write a set of quantum numbers for each electron beyond the noble gas. So titanium is right. Where is it? Right there. Give me a thumbs up when you're done. Okay, so there's the electron configuration using the noble gas and orbital box notation. Notice I'm not using boxes, I'm using lines. So here's one little thing I should correct on this to make it look better. I'm going to use a little bit of white out here. So I should have 5 orbitals. 1, 2, 3, 4, 5. Okay, so for these electrons, I'll call them 1, 2, 3, and 4. 1, 2, 3, and 4. N, L, M sub L, and M sub S. I'm going to start with M sub S. This one's plus 1/2. Number 2 is minus 1/2. 3 is plus 1/2, and 4 is minus 1/2. Because arrow up is plus, arrow down is minus. For the N, these first 2 are 3s, these second 2 are 4s. For the L, D is equal to, let's see, S is 0, P is 1, D is. That doesn't work. I got to try that again. S is 0, P is 1, D is 2. S is 0. So those are the L's. Now all I have to do is put in the proper M sub L. Well, if L is equal to 0, M sub L has to be 0. If M sub L is 2, it could be -2, or it could be -1 or 0 or +1. I could choose any of the 4 numbers or 5 numbers I want. Now here, I made a mistake. Do you see how I called that one +1/2, -1/2? It should be +1/2. Here, the M sub L has to be different because these are 2 different orbitals. So I can choose -1, I can choose 0, +1, or +2. But these have to be different because these orbitals are different. Are you guys clear with the set of quantum numbers? I'll give some more quantum numbers for 1. 1 could also be 3, 2. Actually, I'm going to give more quantum numbers for 2. Given that 1 is this, 2 could be 3, 2, 0 +1/2. It could be 3, 2 +1/2 +1/2. It could be 3, 2 +2 +1/2. In addition to this one here, it could be any one of 4. Are we good with this? Okay, then let's move on. Next problem here is subshells, energies, and electron assignments. Which of the following statements correctly describes the effective nuclear charge felt by the 2s electron at a large distance from the nucleus? So in general, when we take a look at Z star for an atom, the NS has a larger Z star than an NP, has a larger Z star than an ND, larger than an NF. And it's for this reason that the NS is more stable. The Z star, the effective nuclear charge, the larger it is, the more stable the electron. Okay, so here, Z effective within an atom looks like this. What happens to Z star as you go between different atoms? In general, when you go across a period, Z star increases. Why? Because when you go across a period, you get more protons in the nucleus, which improves your Z star. In a group, when you go down a group, Z star decreases, or excuse me, also increases because you're getting more electrons. Okay. So let's take a look at this. The 2s electron at a large distance from the nucleus, they're asking what is the effective nuclear charge felt by a 2s electron? So the deal with the 2s electron is if you have a 1s and a 2s, and you have 2 electrons here, and here's your 2s electron, when it looks at the nucleus, if you have 3 protons here, this guy sees a +1 because these 2 block part of the charge. And basically you just add them up. 3 protons plus 3, 2 electrons minus 2. Plus 3 and minus 2 is 1, so this guy sees a +1. Now, if we take this electron and move it over here, what does it see? The electron sees a +3. Now, where does the electron spend more of its time? Inside or out? And the answer is out. So what's it going to see mostly? It's going to see mostly a +3. So at a large distance from the nucleus, the 2s electron is going to see a Z star equal to 1. So this is a large distance. The other question you could ask with this particular problem without rewording it too much would be, what charge will the 2s electron see when it's really close to the nucleus? The +3. And this should be for a lithium atom. Okay, the 2s electron at its most probable distance from the nucleus. So at the most probable distance from the nucleus, what will it see? The most probable distance is over here, so it's also going to be a +3, or excuse me, a +1. At the closest, it's going to be a +3. Okay, so this has to do, so the effective nuclear charge is kind of a weighted average of what the electron sees based on where it is relative to the nucleus. And a 2s electron is more likely to be farther from the nucleus than close to the nucleus. Okay, the values of N and L are useful to determine the order of filling, which is the Aufbau principle. Use N and L to determine which orbital will fill first. So this is something that the book wants you to know. I've never really used it, to be honest with you. But the deal is the lower N plus L is more stable. Ties go to lower N. So if we look at 4F, 5D, and 6S, 4F is N4, L 0, 1, 2, 0, 3. 5D is a 5, and D is a SPDF 0, 1, 2 is a 2. And 6S is a 6, and S is a 1. So when you look at the total, you get 7, 7, and 7. So which one is the most stable out of all of these? And the answer is the 4F is more stable than the 5D, is more stable than the 6S, because the tie goes to the lower end.
Wait,
Any questions on that one?
Wait, isn't S 0 for the L?
Oh, you're right. Thank you. So this is a 6. So we're looking at 6S, 4F, 5D. Good catch. Good catch, Harry. I did the old mistake. S is 0, and I go S1, P2. You got to start at 0. S is 0, P is 1. I think that whoever decided that those should be the quantum numbers, Schrodinger or whoever, did that on purpose just to mess with us. So any questions on this one? Okay. Now, we don't need to worry about this if we follow the block method. Okay. Next one. Let's see, how many more of these do I have? I have 2 more. We'll see if we get through both of them. If we don't, I will be Zooming on Wednesday, even though it's a holiday. You don't need to attend, but I'm going to be there. Okay, electron configurations of atoms and ions and magnetic behavior. So using orbital box diagram, depicting electron configuration for each of the following ions. So to get the electron configuration of ions, we have a special set of rules to follow. So for the electron configuration, there are 2 sets of things that we follow. It depends on whether the ion is a cation or anion. If it is an anion, the electron configuration is the same as the noble gas in that period. So if we look at these anions, the oxide anion, the nitride anion, the fluoride anion, their electron configuration is the same as neon. So the anion is clearly really easy to do. It's the same as the noble gas in the same period. For the cation, first thing you do is you read, so we do that Aufbau filling order. Then we rearrange. And then we take away the least stable electrons equal to the charge. So I'm going to show you how to apply this to some of these. So these are all cations until we get to fluorine. So let's do fluorine first, which is D. Fluorine is 1s2, 2s2, 2p6, which is the same as neon. And I should say that's fluoride ion. Any questions about the anion? Are we good on the anion? Okay, let's look at sodium. So sodium, first step is 1s2, 2s2, 2p6, 3s1. There's no need to rearrange, so I'm going to say that this is 2 also. No need to rearrange. And then, since it's a +1 charge, we take away 1 electron, the 3s. So we get 1s2, 2s2, 2p6, which also happens to match the electron configuration of fluoride ion and of neon. But you'll notice I did not say that the rule for cations was to make them match the preceding noble gas. I didn't say that. And when we do B, you might think, well, why not? So here's aluminum, 1s2, 2s2, 2p6, 3s2, 3p1. No need to rearrange. And when we go to aluminum with a +3 charge, we have to take away 3 electrons, 1, 2, 3. It's the same as neon. But let's look at germanium, the next one that they want us to do, with a +2 charge. So neutral germanium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and then 3, 4, 5, actually 2, 3, 4, 4p2. So that's germanium. We have to rearrange. So 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p2. And then for the +2, it becomes 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2. You take away these p electrons. Now, take a look at this. This is not the same electron configuration as argon, which is the noble gas that precedes germanium. So that's why I give you a different set of rules for for cations and anions, is that some of the cations end up with a noble gas configuration, but a lot of them do not. So the best way to get every cation is 1, get the neutral atom. 2, rearrange. 3, take away electrons equal to the charge. And there you go. So are we good on that? Getting the electron configuration of ions. Okay, so here, why don't we try this for titanium, titanium 2, and titanium 4. Let's get the electron configurations of these bad guys. So here, notice they say orbital box notation, so we get to start at argon. I know I cheated. I didn't write it down in the filling order and then rearrange. But they don't want this. What do they want? They want noble gas and orbital box. So that means this. So there's titanium. How about titanium plus 2? There's titanium plus 2. And then what's titanium plus 4? It's the same as argon. So are any of these paramagnetic? This one is paramagnetic. This one's paramagnetic. And this one's diamagnetic. Paramagnetic simply means that you have electrons that are unpaired. So this has 2 unpaired electrons. This is 2 unpaired electrons. Diamagnetic means they're all paired. All the noble gases, their electron configurations are diamagnetic. So any questions on this one? We got time for one more, so let's go ahead and do it. Let me see if we have time for these other ones. Probably not, but we'll cover those on Wednesday. So one compound found in an alkaline battery is NiOOH, a compound containing nickel plus 3 ions. When the battery is discharged, the nickel plus 3 is reduced to nickel plus 2 ion, as in nickel hydroxide, nickel 2 hydroxide, I should say. Using the orbital box diagrams and noble gas notation, show electron configurations of these ions. So we're going to go ahead and start with nickel. Nickel is going to be argon, 4s2, 3d8, which rearranged becomes argon, 3d8, 4s2, which becomes argon, 5 orbitals for your 3d, 1 for the 4s. The 3d has 8, so if we put them in there properly, it's 1, 2, 3, 4, 5, 6, 7, 8. And then the 4s looks like that. Okay, so what does nickel plus 2 look like? Argon, 1, 2, 3, 4, 5, 6, 7, 8. So we're going to take away those 2. And for nickel plus 3, what's it going to look like? Okay, so for the plus 3, we have to take away another electron here. And I know that most of you are going to want to take that one, but that's the wrong one to take. You want to take one of the paired ones, because basically when you pair electrons in an orbital, that's not so hot. I mean, it's okay if you're looking at a 3D versus a 4s, but it's not okay when you're looking at a 3D versus a 3D. So these 2 electrons repel one another. This one, since it doesn't have another electron in there, it doesn't repel anything. So we got to take one of these 3 here. And the one you want to take, I always say, is the last one in, first one out. So this was the last one I wrote in. It's the first one out. And that's why I always write them in the way they're supposed to go in according to the Aufbau principle. 1 per orbital before you pair them, and then pair them. So this is the last one in. So any questions about the nickel and nickel 2? Or are you okay with those? How about the nickel 3? Are you okay with that? Are you guys still there? All right, which ones are paramagnetic and which ones are dia? Take a look and assign paramagnetism or diamagnetism to each of these. When you're done, give me a thumbs up. Okay. This one's para because this one's para because they're unpaired. This one's para. And that's it. Okay. We'll do some more problems on Wednesday. Feel free to tune in at noon. I know it's a holiday, but I'm still going to be Zooming. Okay. Turn on your mics. Say goodbye.
Bye, guys.
All right. See you on
Have a good
Wednesday, I
one.
hope.
Yep. I'll probably see you then.
All right. Bye-bye.